So in this tutorial we are going to talk about the heap data structure, and heaps have a lot of applications in computer science, and because heap is also it takes a less time complexity than other data structures in some certain operations like insertion, deletion. So we will talk about that in a later bit, but first let me just define what exactly a heap is. So a heap is just an array heap is an array that is visualized as a nearly complete binary tree. So talking about the heap data structure, what we are just going to do is we are just going to visualize the given array as a nearly complete binary tree. So we have discussed about the binary trees in the previous tutorials, and we know what exactly is a nearly complete binary tree. So let's take an example and see how we can convert or how we can visualize. It's just a visualization. We are not converting an array into a nearly complete binary tree. We are just visualizing it. So let's see what is the meaning of this line by using an example. So let's suppose I have an array, and let me insert some of the elements in this array. 16, 14, 10, 8, 7, 9, 3, 2, 4 and 1. So let's suppose we have an array with these elements in it, and we know that the indexing of an array starts from 0. So I will write the index positions here: 0, 1, 2, 3, 4, 5, 6, 7, 8 and finally 9. So this is our array, and now we're going to visualize it as a nearly complete binary tree. So let's see how we can visualize it as a binary tree. To visualize it as a binary tree, we know that our binary tree has the first element as a root. So we are going to initialize the value of I equals 0 as the root element of our binary tree. So the next element, which is 1, which is at the 1 position of this array, will get inserted at this place. And the next, so this is I equals to 1. The next value, which is I equals to 2, will get inserted at this position. And then similarly, I'm going to add some more elements, like I equals to 3 will get inserted here, I equals to 4 will get inserted here, 7, and similarly 9, 3, 2, 4 and the last one is 1. And I will write the index position of the array here so that we can reference all the nodes of this binary tree. So you can see how we have used the index position of the given array. Let's suppose this is our array A. So we can see that clearly we have used these index positions to create a nearly complete binary tree. So this is a nearly complete binary tree. So I'm going to write here an algorithmic approach to represent or to visualize an array or any array into a nearly complete binary tree. So there are 3 points to remember. The first one is that the first element of our array, which has the 0 index position as 0, is going to become the root of our binary tree. So if we want to visualize our array, we're just going to initialize the first element of our array as the root of the tree. Second, for the parent of I, we're going to do something like this. So let's suppose we take this element at the position I equals to 1, which is 14. So if we want to get the parent of a particular node, we will just divide the position by 2. For example, if I want to calculate the parent of this node 3, I will just divide its index position by 2. So the index position comes out to be 3. So I will write -1 here. So if you will just use this algorithm, or I should say this operation, then you will be able to get the parent of any particular node. For example, if you want to get the particular node of this element 10, element 1. So now if you want to get the parent of this element 1, I'm just going to divide the index position by 2 and subtract the value by 1, which evaluates to be 4, and 4 is the parent of this element 10. So this is how we are going to visualize our array. The third step is that the left child of any particular node or any particular element at index position I will be equal to 2i plus 1. So let's suppose this is the element. Let's take this element 8. So if I want to calculate what will be the index position of the left child, I will just use the index position I, which is 3, and I will just put this in this formula, which is 2i plus 1. So 2 of 3 plus 1 will give 7. So you can see that the left child of this particular node at index position 3 is 7. So we know that for this particular element, the left child is 2. So to access that left child, we will use this particular formula, which says 2i plus 1. To calculate the right child of any particular element which has index position I, we are just going to write it like this, 2i plus 2. So let's suppose I want to calculate what will be the index position of the right child of element 10. So in that case, I will just access the index position of 10, which is 2. I will put this in this formula, 2i plus 2, which is 2 multiplied by 2 plus 2. So this evaluates to be 6. So you can see that the right child of this particular element is at index position 6. So using these 3 formulas, we can actually visualize an array as a nearly complete binary tree. So you can see that we have not actually created a binary tree. We are just using the index positions of the array, and we are defining these index positions as parent, left, and child using these formulas, using these 3 important formulas. To calculate the parent child, you will just divide it by 2, and then you will subtract 1. Then to calculate the left child, you will just multiply the index position by 2 and add 1 to it. And similarly, you can calculate the right child. So in this way, this is the visualization of our array as a heap. So if you have any array, now you can convert that array in a complete binary tree, in a nearly complete binary tree, using these three formulas. And we know that the root of the tree is at index position 0. So this is what exactly a heap looks like. And most of the operations like insertion and deletion takes a time complexity of log of n. So this is big O of n. Big O of log n. So you can see that this is a very good time complexity, and heaps are used to just insert, and if you want to insert any element or delete any element, you can just visualize an array as a heap data structure, and you can add or delete any element, and the time complexity will be big O of log n. So the main application of the heap is seen in the priority queues, and we have already studied about queues data structure. We know that what is the principle of a queue. A priority queue is just a queue. Let's suppose this is our queue. Our priority queue is just a queue that has for each element of inside the queue, we are assigning a priority to it. So the higher is the priority of a particular element. Let's suppose we are assigning this element as a high priority of, let's say, 1. So this element will get popped out from the queue, or maybe get inserted inside some other queue. So the main reason or the main application of heap is the priority queues, because it takes very less time complexity. So let's discuss about two important heap properties. So there are two heap properties, or you can say the two different types of heaps are there, and we will see how we can create these two types of heap. So the first type of heap is known as the max heap, and the second type of heap is known as the min heap. So let's see what exactly a max heap and a min heap is, and how can we actually convert an array into a max heap or a min heap. So let's talk about the max heap first. So max heap is a special type of heap which has the following property known as the max heap property. So in a max heap, the key of a node, or you can say the data of a particular node, key represents the data, not the index value. So the max heap property says that in a max heap, the key of a node will be either greater than or equal to or equals to the keys of its children. So this is known as the max heap property. So if any heap, or you can say if there is an array which you are visualizing as a heap data structure, if it is following this property, then we can say that the heap is a max heap. So in this previous example, let's see whether this is a max heap or not. For the max heap property says that the data of every node will be greater than or equal to the keys of the children. So you can see that in this example, if we take this node, so the value 16 is greater than 14 and 10. So similarly, if we take any other value or any other node, we can see that the values of the children are always less than the value or the key of any particular node. So this is indeed a max heap. So this is an example of a max heap. So let's see what is not a max heap. So let's suppose we have an array 2, 4, 1. So if this is an array, we can see the index position is 0, 1 and 2. So to visualize this as an heap, so we are going to convert it in a nearly complete binary tree or a heap. So we know that the root element is the first element, so I equals 0. So the left element will be 4, which has an index value 1, and this will be like this. So using the heap visualization, we have created this nearly complete binary tree. So is this a max heap? So the answer is no, this is not a max heap, because if you will see this element 2, the value of its child 4 is greater than its value, which is violating this rule. So this is not a max heap. So what we are going to do in the implementation part is we are going to create a function which is a max heapify function, and this function will take an array. Let's suppose the array is A, and what it is going to do is it will just max heapify the given array. So let's suppose we have an unordered array. The build max heapify function will just max heapify this binary tree. So after the call of the max heapify function, our binary tree will become something like this. So now you can see that the violation of the max heapify property has been corrected by swapping the values 2 and 4. So this max heapify function will perform such an operation, and it will do it recursively. So it will call itself again and again. Like it will first call it for the value of I equals to 0, and then for 1, then similarly 2, and so on. So this max heapify function will just perform recursion, and after every recursion, or I should say after every call of this max heapify function, it is going to correct a single violation. So a single violation means that you can see that here there is only one single violation. If we have a further big binary tree like this, I'm not adding any elements inside it. I'm supposing like there are more elements in this tree. So we will have to call this max heapify function again and again, and this is recursion. We will just use recursion, which we have also used in binary trees before, but this time we are going to correct a single violation, and correction just means that if the max heapify property is violated, we are just going to swap the values of the two nodes. So we will use this max heap property. The next property is the min heap property, and in the min heap property we are just going to reverse the comparison, and the key of the node should be now less than equal to the keys of its children. So we are just going to change this comparison, and we will get a min heap. So what will be the time complexity of this max heapify function? So since this the time complexity of this max heapify function will be big O of log n, and the reason why it is big O of log n is because it is performing a recursion, and we know that the recursion in a binary tree is having the time complexity of big O of log n. So in the implementation part, which is we are going to do in the next tutorial, we will just create an array and we will just visualize it as a heap, and we will just create a max heapify function. And in this max heapify function, we are just going to call this function from I equals to n by 2 minus 1 to 1, sorry, to 0. And we are going to call this max heapify function again and again with the value a comma I. So in the implementation part, we will just create a max heapify function which will be called from I equals to n by 2 minus 1 to 0. That means that we are calling the max heapify function from like this, from down to up. And why we are starting from I equals to n by 2 minus 1 is because we are ignoring the max heapify function should not work on these leaf nodes. So we can see here that if we want to calculate the nodes, you can see that there are 5 leaf nodes here. So it is equal to, the leaf nodes are equal to n by 2 minus 1, and we do not want to perform the max heapify function on the leaf nodes. So that is the main reason why we are running this for loop from n by 2 minus 1 till 0. So this max heapify function will call itself recursively, and after each call it is going to correct a single violation. So in the implementation part, in the next tutorial, we are going to implement this max heapify function, and the main reason why we are using this max heap is because we are going to implement heap sort, and heap sort takes a time complexity of big O of log n. So in the next tutorial, we are going to use this max heap property. We will create a max heapify function, and we will use this max heap to sort our given array. So if our array, we will provide an unsorted array to the heap sort. So we will provide an unsorted array to this heap sort, and it will call this max heapify function, which will just create a max heap, and then after creating the max heap, we can easily get our sorted array like this. So thanks for watching.